Hey there, we've got a Codeforces round today. It's educational round 110. And we're getting started. All right. Playoff tournament. Oh, what happened? Okay. Oh, okay, that's super easy. Okay, so the only benefit you get is from putting even things first. Okay, sure. Zero, one, question mark, 0 and 1. Okay. Okay, substrings. Substrings, it's like, okay. So it's beautiful as long as there's a conflicting 0, conflicting 1, and conflicting. Okay, so, okay. guess I don't need this. XP plus comma 2 equals P and S equals constant of X or in positions P. Okay. This is just bool, right? And this is beautiful. Yep. Oh, did I take that long? Let's see. All right. Anyway, I could have made this linear, but whatever. One versus 2, 3 versus 4. So 0 means left, 1 means right, mark means either. Okay, yeah. Yeah, so you just have DP values in your tree. And you just need to update upward. Wait, that's fun, I guess. Yeah. If SS, if it's 0, that means you have to go right, actually. So one thing's left. And it's both. 14. Oops. So, I do actually want to do that then. So this should be 0. Okay. Cool. We just got E and F. What cause difference? Cos gets Okay. Okay, this is a weird problem. I guess you can just walk down the tree because once you finish buying, it's gone. So you just need, you just have a bunch of zeros and you need to quickly figure out, okay, where's the first one? These jump pointers here again. You can have a non-zero and a 0. How does that? Oh, one path. Here to here. No, I can't have it, right? How did you buy from here when you didn't buy from here? No, that's not possible. Yeah. So yeah, we just jump over every binary search up until we find we just start there and start going. Oh, we need to know which child to go to.
We don't really have to do that. Okay.
No, I don't need to actually. Actually don't even have to, yeah, okay. Oh, what is this return? The amount of coal and the amount of money. So that's what I'm gonna do. We don't need the highest bit because we already have this log thing. Campus. Someone on top of this. So many times. Okay, and now not we want is W. Change this W and A of no. I'm just gonna do it. I actually don't need to. W. How did that happen? This feed doesn't exist, what? Oh. Oh, ew. Okay. So we need a compress map or something like that. Okay. Only for B. Oh, never mind. Alright, what's this runtime error? What is this runtime error? Oh no. That's what it is, isn't it? I hate this input format. Okay, I think I got it. I mean, if it's possible to one, you just start the entire thing. Okay, why is this hard? It's 0 for the same. Okay, why is this hard at all? Oh, it might be 1, it might be 2. Oh, I see. So it's always at most 2. Oh, I see. So it's number 0. Okay, I understand. It's number 0. Either n is small or s length is small. So if n is small, you just do it. The length is small, what do you do? You can go over every substring in your array. Every sorted substring. There's only 50,000 strings. You know what to do. So we're going to group them. Now we're going to subtract one of these from every pair we get. guess you could just compare it by the way. Where is that? Oh. I need to capture here now. Yeah, either of these is sorted. The answer is 1, otherwise it's 2. Apparently. The backhash. Yeah, and otherwise we're gonna I might have to use string hashing. I guess I'll string hash. Just copy all this. I don't think I need these steps. Cat hashes. I don't think I even need that. need a hash map. Oh, is this gonna take a lot of memory? I do get a lot of memory. How many entries do we have in here? Oh. That was totally wrong. Okay. So let's restart it. 25. This divided by 2. — 31 million entries. That is way too many. Oh, man. I need a solution that doesn't require a hash map. This is not equal. And this is not equal. That's right. Hey, if I sort it, is that a string? Is that one of my strings if I sort it?
Okay, that's not as bad.
And then you're just looking for does this cat hash this? Oh, is that? Oh, you do that. Or like this can cache, this frequency table needs a cache. I guess you can do that. Oh, but then no, that makes the hash table huge again. I don't want to make the hash table huge again. So we cannot do len cubed. It's not an option. 15 million. This would fit. The runtime would be 100 million. Maybe I can do this. I thought it was 24. Right? Where did I get 10? Oh, 1 plus 2. No, it's not. That's already with this. Okay, so. Did I forget to do something? Oh, so wait, maybe I'm gonna Okay, maybe I guess I want to shuffle like a middle section. Yeah, it looks better. Okay, so now it's fine. Yeah, okay, so $40. Maybe I'll go 4,050. Even this is fine. This is like 400 million. I guess that's fine. I do need, okay, so I do need to do this. $20,010. That's pretty right. That's not even generated. Okay, so 12, 16. That's also not generatable. And now we're getting to the two really small strings, so actually this is fine. This actually still is fine. This is like 500, right? $100. Alright. So now these strings are like absurdly small. So yeah, we really just said, okay, yeah. Honestly, we just do cubic. Oh, let's just do it. Yeah, let's do it. If string I not equal to other I, then string. You save one if oh god, what is that? That's not what I want. Point 249. Okay, so 0.249. I guess we want to. Something like this. Oh, I don't use this at all. I can just delete all this. Let's submit it. Okay. All right, just finished the round. And yeah, right now we're in third, and there are still 2 people here who could pass us. So should end up somewhere between 3rd and 5th. And now that we're done, we can go through each of the problems. So yeah, let's just do that, starting with problem A. So, okay, so problem A is kind of a precursor to problem. Oh, what just happened? Something's wrong with this problem page. Anyway, problem A is kind of a precursor to problem D. They both have this playoff tournament idea, like a bracket tournament. But in this problem, there's just 4 players. The first will play against the second, and the third will play against the fourth. And then the winners of each pair will play the finals. You know the skill levels of each player, and they're always different, and always it's always the case that the better player wins. So there's no upsets, and the tournament is fair if the 2 players of highest skill meet in the finals. So to just determine if it's fair or not. And yeah, this is super simple. It's basically just you know, let's take the max of these 2, and let's take the max of these 2, and those have to be the 2 highest values. So the way I did it was, I guess I will pull up all the code. I just read an ABCD. I made a sorted version so that I could figure out the 2 highest values. The 2 highest values are sorted 2 and sorted 3. And then I just made sure that like max AB plus max CD is equal to the sum of those. Yeah, another thing you can do, you can just make sure that the top 2 aren't both in the same half. There's a bunch of ways you can do this, just gotta find the right. Okay. That was the crash there. Just gonna make sure you find a good way to do it, and then yeah, just print yes or no. So pretty simple problem there. Now in terms of problem B, you've got an array of n integers, and a pair of indices ij is good if I comes before j and the GCD of ai and 2 times aj is greater than 1. So find the maximum number of good pairs if you can reorder the array in any way you want. So this is almost just GCD of ai and aj is greater than 1. The only difference is this 2. And if it were actually GCD ai aj greater than 1, then there's no reordering that helps, because each pair, you know, it's just, is there a common divisor or not? But because of this 2, another way that we can satisfy this is if ai is even. If ai is even, then we're always good no matter what ai and aj are otherwise. So basically the problem here, the way to solve it, we just end up doing a simple greedy idea. The greedy idea is, well, since I has to come before j, we can just take all of the even numbers and put them at the beginning of the array, and then all the odd numbers after that. And the reason for that is basically that way any pair with at least one even number will always be good, because if there's only one even number, then it'll be even first and then odd, and then this pair will be good. And so like that's essentially the best thing that we can do with this condition. And then the reason that n, so you can just order them that way in O of n super quickly. The reason that n isn't too big is because we actually have to calculate the number of good pairs, and then so that way we just end up doing a bunch of GCDs, and it turns out to be fine. Yeah, so at first I sorted everything by their mod 2, which just puts evens first. And then I guess it's good there are no negative numbers. That could be tricky, because -5 mod 2 is actually -1 in C++, which is kind of annoying. But anyway, that's not a problem here. We're just going to sort, and then we're going to calculate the GCDs. We're just going to do what the problem statement says. If that's greater than 1, we're going to add 1, and we'll print that out. And that's it. Pretty simple one. Yeah, just one main observation there, the evens first, odds after. Okay, so problem C, unstable string. So in this problem, A string is called unstable if it consists of 0 and 1, and it's always alternating. So it's 0, 1, 0, 1, 0, 1, or it's 1, 0, 1, 0, 1, 0, right? And then a string is beautiful if it consists of 0, 1, and it can also contain question mark. And you can replace the question marks to either 0, 1 for every character to make the string this unstable string. So for example, this is beautiful because you can replace it with 0, 1, 0, 1, 0. 0 itself is beautiful even though it doesn't have any question marks because it just matches an unstable string. So any unstable string is already beautiful. And then, of course, anything that's all question marks is beautiful because we can pick, either of these two options, 0, 1, 0 or 1, 0, 1. And then 0, 0 is not because there's no way to make that work. And then similarly, this is not because no matter what you do, these ones are spaced an odd distance apart. So that's one big observation there. And we're given a string s, which can be pretty big, 2e5 in length. And we need to determine basically how many substrings of s are beautiful. Okay. So we've got a key observation from here. Basically, there are a couple different ways to make a substring not beautiful. The first way is if there's any pair of ones or any pair of zeros that are an odd distance apart. Because then there's no way we can fill in the whole. For example, here we go 1, 0, 1, and then we mess up on this one. And then, yeah, so we can start thinking about parity. Parity means even or odd. And that condition really just means that there are two ones on opposite parity indexes or indices. So that's one way to be invalid. Another way to be invalid is that there could be a 0 and a 1 on the same parity index. So there's a 0 on an even index and a 1 on some other even index, and that would be a problem. Yeah, and then if you think about that, those are really the only types of problems you can run into. So just a couple of different things to check. And now we need to think about how to count substrings that have that don't have any of these problems. So one key observation here is if a string is beautiful, then any substring of it is also beautiful. And that's pretty obvious from the definition because, if we have a way to replace the question marks to 0, 1 to be unstable, then we can just, take the substring and just cut it off and it'll still be unstable. So that gives us a nice idea here where in my code, what I actually did was I picked the start point, I iterated over the start point, and then I binary searched for the end point. But you can actually just do this as a two-pointer sweep. So let me see. So maybe I'll actually code that in a second. But the really key function here is to determine whether a substring is beautiful, and that's right here. So first of all, I do prefix counts in order to, because I want to be able to count, okay, in this substring, how many zeros are there in odd positions, for example. So I have this 2x2 table of prefix counts. So x means are we looking at 0 or 1? And p means the parity of the index we're looking at. So for example, prefix count 1, 0 will tell us the number of ones in even positions. And that's what we do here. And it tells us that count in a prefix. So essentially we're just counting, okay, is I mod 2 equal to p and si minus 0 is equal to x. And now we want to know, now we can use this to implement exists. Exists tell us for the substring from start to end, is there an occurrence of x at an index of p mod 2, an index mod 2 of p. And that's done by counting. So we just count the number of things in between this range. And if it's greater than 0, then it exists. So this can tell us, for example, given this start to end substring, is there a 1 at an odd index? Okay, and then using that, we can write this beautiful function. So we just implement the problems that I explained before. So if x exists at an even position and it exists at an odd position, then we have a problem. So we return false. And then the other thing that can happen is 0 exists at a certain parity, and 1 also exists at that parity, and that would be a false. And if neither of those is the case, then it's true. Then it is beautiful. And so I just, using this function, I just did a binary search. But you can also do it with the two-pointer sweep. So I guess just for fun now, I will re-implement it with the two-pointer sweep. So basically, while that's it. Okay, cool. You know what? I can actually even submit it again. And it won't hurt my penalty because this is ICPC style. Okay, and it's accepted, and I mean, I guess it's not noticeably faster because it was already super fast to begin with. But anyway, there we go. So this is actually O of n, which is nice. Okay, and then now we're gonna go, yes, problem D. So problem D is like a bigger version of problem A. We've got this playoff tournament. There are 2 to the k teams, and then they're facing off in this bracket format. You can see what it kind of looks like here. Relatively self-explanatory. If you've seen any sort of bracket tournament, you should know what this looks like. And ultimately, the winner of the last game is the winner. So it's just a single winner's bracket. There's no loser's bracket. And yes, so we know what happened in each of the different games, but some of them are potentially unknown. So we might know that, out of this game, the top player won. This game, the bottom player won, but this game we don't know what happened. And we want to know, the thing we care about is the number of possible winners of the tournament given the string of information that we know about each of the games. And yeah, so we're given the starting state of the string, and we need to do Q queries of the following form, which is to change a character in the string and then print fs as the new result. So, well, let's think about, given a particular s, how do we solve the problem? So basically we're doing a kind of a DP where this bracket is actually just a tree, right? It's just a, what is it called? Perfect binary tree. I think that's the right term. Yeah. It's like a complete and full binary tree. Yeah, perfect binary tree. Anyway, so it's essentially just like a tree DP. For every node of the tree, we can keep track of, okay, how many different players could win this part of the tree. So for example, if all 3 outcomes here are question mark, then the DP state at this point would be 4, because it could be anywhere, any team from 5, 6 to 7, 8, right? But let's say here we had a 1, here we had a question mark, here we had a question mark. Then the answer would be 3, because we know that 6 beat 5. We don't know if 7 beat 8, and we don't know what happened here. So it could be any of 6, 7, 8, but it definitely can't be 5. And so the DP is actually pretty simple. So at a given node, if it's question mark, then the DP value here is just the sum of the DP values here, because either of these could end up winning this game. If the DP value is 0, then if the string value is 0, then the DP value here is just the same as the DP value here, because we know that this side is the winner. And then if it's 1, we just take the value here because we know that this side is the winner. So we have a pretty simple DP that we can just start from the leaves and propagate up to the root to get the answer. The thing is, we have to do modifications and we have to update the answers. So obviously, and k is big, 2 to the k is quite big, so obviously we can't recompute the entire tree every time. But it turns out, because of the kind of dependencies, the way that works, when we update a node, for example, let's say we update this node, well, this value will change, right? And then the only other things that change are the ancestors of that node. So this value has to be updated, and then this value has to be updated. But we don't have to update this because it doesn't depend on this guy, and we don't have to update this either. So it's only the ancestors. And so that way we only have to update a log amount of nodes, or rather roughly k, right? And that makes the solution really fast. And that's how you do it. So here's the general code. So I did some kind of indexing ideas to make it a little easier to deal with. So instead of game 7, I call this game 1, game 6 is game 2, game 5 is game 3, and so on. And then you get the nice segtree pattern of if you have game X, then, or node X, then the two children are 2x and 2x plus 1. And yeah, so that's basically the idea. So this is a function to basically solve the dp value at x. If x is a leaf, then it's just 2 if it's question mark and 1 otherwise. If it's not a leaf, then we take the value and we decide which child to go. And because of my indexing, it ends up being a little bit flipped around. 1 means 2x and 0 means 2x plus 1. And then yeah, question mark means add up the both of them. And then if we update a value x and we want to propagate it up, this is how it works. You just update x, divide by 2, and repeat. And yeah, so that's pretty simple. And then this is the initialization. So for every x, basically from the leaves all the way to the top, call update on x. And then with each query, we're gonna change that index. I also have the string reversed. So we're gonna change the index and then propagate it up, and then the answer is always dp1. So that's the key idea. The main thing to realize is that, first of all, you realize how do you solve a single string, a single instance without queries? And then you realize how do you update the string without redoing the entire thing. All right, problem E. So problem E has a tree. Yeah, the problem's a little long. I'm not going to read the whole problem, but basically, each node has a certain amount of gold, and the gold costs a certain amount at each node. And you're also guaranteed that basically the cost is cheaper at a parent than at the child. And these are nodes in a tree. And these nodes are added one by one. So this is kind of like online interactive style where you can have new nodes added and you can have queries to buy gold. And when we buy gold, it looks like this. Essentially, you take a path from the root to VI, and we need to purchase WI tons of gold from the vertices on this path where we spend the minimum amount of money. And if there isn't enough gold, we just buy all of it. So because of this guarantee, that means we have an obvious greedy strategy where we would prefer to buy at the root, and then at the root's child, and so on. And the last node we would want to buy from is VI. So we kind of buy in that order because of the order of the costs. And yeah, so basically there are two types of operations. One is to add a node, and one is to buy gold from vertices on the path. Now you notice there's no way to add gold to a vertex. So once you finish buying a vertex, that can only happen once for that vertex, and that vertex is done. You'll never buy any more from there. So one key insight that I had was it's okay to take time proportional to, for example, O of number of vertices, number of different vertices that I actually buy from. Because if I buy from 100 different vertices, then I actually exhausted 99 of them, at least. So 99 of them, went from positive to 0, and they're just kind of done, right? So it's okay to just walk down and buy from each point. But what's not okay is it's not okay to spend a bunch of time going through a bunch of zeros and making no progress. So you kind of need to jump quickly to the non-zero nodes on your path. And then the next insight is that it's not possible for one node to have a positive amount of gold and then its child to have 0 gold. Basically, if you think about the path, there will be some amount of zeros and then some amount of positives, and that's the only thing that's the only way it can look like. And the reason is, if you think about the case where a parent has a positive amount of gold and the child has 0 gold, well, we would have, there had to be some point where we bought all of the gold from that child, but because of this path setup and because of this condition, that cannot have happened without buying all of the gold from the parent first, because the parent is cheaper. So that condition, or that scenario, can never occur. So yeah, we just need to quickly kind of find the point where the first point on the path with positive gold, and we can just walk down from there. So the way I did this is I actually just set up a bunch of 2 to the k jump pointers for ancestor, like the 2 to the kth ancestor of the node. And so when we add a new node, we know the parent, and then we get the 2 to the kth ancestor for every k. And it just looks like, okay, if ancestor k minus 1 doesn't exist, then it's just -1 because it doesn't exist. But otherwise, it's going to be the k minus 1, 2 to the k minus 1, 2 to the k minus 1 ancestor of the 2 to the k minus 1 ancestor. And this is kind of the standard idea in doing jump pointers. And when we do that, now what we can do is when we get a query, we have v, right? We can actually binary search upward for how far can we go while keeping the amount of gold positive. So we can take k from log minus 1 down to 0 and say, hey, if the 2 to the kth ancestor of our current node still has gold, let's go up there. And then up just says the amount of steps we went up. You have to, you do have to end up dealing with, oh, how do I walk down the path? Like, how do I find which child of this current node keeps me on my path? And the way I just dealt with that by actually just repeatedly using this get ancestor. So I don't actually walk down, I just repeatedly walk up from v again and again. And I start from up and I go down. And then, yeah, the rest is just kind of implementation, making sure you don't take more than W or a node. And also if W hits 0, you want to break, so you're done. But yeah, and then there's some annoyance of, I really hated how this problem did the indexing for the nodes. You have to do this ugly like compressing, because you have to take the query index and compress it into a node index. And I missed this, and that gave me a wrong answer, or a runtime error actually on this problem for a while. But anyway, once you take care of all the details, then you're good. Let me check the standings. Okay, so geothermal passed me, so I am now in 4th, and I think, yeah, I'm definitely safe in 4th now, assuming I pass everything. So yeah, I guess that's right in the middle where we were thinking. Okay, so problem F, string distance. Okay, so you're given 2 strings A and B. You can apply the following operation any number of times, choose any contiguous substring of A or B, and sort the characters in it. And FAB is going to be the minimum number of operations you have to apply in order to make the strings equal. Or if it's impossible, they just make it 1 through 37 for no particular reason. So examples, FAB, AB is 0. They're already the same. FBA, AB is 1. We can just sort this and make it AB. FEBCDA and ECDBA is 1. We take the CDB, I missed a little bit. All right, CDB, and we sort it, we get BCD, and then they're the same. You're given n strings that have equal length. Oh, I guess I missed that they have equal length. It doesn't actually matter. N strings having equal length. Calculate the sum for every pair of their f. Okay, and n is up to 2e5, and actually the total length of the strings is up to 2e5. So when you see something like this, the first thought that should come to mind is, okay, basically if this is the case, then either n is small or the length is small. One of those has to be true. And by small, I mean less than the square root, or at most the square root of this number. Yeah, and so a couple insights that you need into this problem. First of all, there's no way, if you have 2 strings A and B, the only way that you could ever make them the same is if they have basically the same frequency of characters. So if you sorted both strings entirely, they would be the same. And actually, that observation, sorting both strings completely, means that if it works, the answer is never more than 2. And then we don't have to worry about f being equal to 0 because all the strings are pairwise distinct. So basically, if it's possible, it's either going to be 1 or 2. 2 is from sort A and then sort B. And then in order to get 1, what that means is we have to pick some substring of A or B. Let's say we pick B. There's going to be some substring we pick of that and sort it. So what that means is the prefix before that matches in A and B. The suffix after that also matches. And then maybe I'll pull up one of these as an example. So here are some test cases. Maybe I'll do the 15. Okay. So for example, let's just take these first 2 strings. Let's say this is A. What is this? Okay, this is A, and then this is B. Apparently, okay, this is B. And for this, basically what we would do is we would take this substring and sort it. And if you actually tried it, you would find out that it would be the same as this C, E, E, F, all the way to X, Z. And now this suffix matches this suffix, and then this prefix matches this prefix. So that would actually be doable in one sort. And so that's kind of the case that we're looking for here. So the way I did this was I actually had 2 different algorithms. So basically, like I said, either n is small or length is small. So you want to find good algorithms for both cases. In the case of n is small, what I did is, well, we just described a way to solve a pair of strings, right? We find out how long their prefix matches, we find out how long their suffix matches, and then if either of the 2 is actually sorted in between, then the answer is 1. Otherwise, it's 2. And we're already assuming that the strings are already the same set of characters, and that's handled by this map for grouping. The way I do that is I read in the string, and then I sort the string, and then I put it into a group based on its sorted version. Okay. Now, yeah, if we can just solve a pair, what that means is we have an easy n squared times length algorithm, which is just iterate over every pair and then solve the pair. Since this solving pair is O of length, and this loop is obviously n squared, this is going to be n squared times length. And the constant factor on this is really good, so I actually ended up doing this as long as n is not like crazy huge. And then the other version is, okay, if the length is fairly small, we have another thing we can do, which is basically if we think about this case that we had, we want to know if we can take some substring and then sort it and then get a different string that is also in our list. So in particular, if we look at the substring we're sorting, well, in order for this to be like a maximal suffix and prefix, what we need is that, first of all, this character does not equal the character of the sorted version. So maybe I'll give a simpler version. Let's say we have AAA, and then we have IHG ZZZ, right? And we're considering this substring. Well, if we sorted it, it would look like GHI, right? And so we just want to know, does this string exist in our lists? If so, that is one pair that we can save one on. And now if we think about taking some larger substring like IHGZ and sorting it, we would actually get the same thing. So that's a problem with double counting. But we can notice is that in that case, this Z still matches this Z, so we actually didn't need it. We could push it to here. So basically we can avoid this overcounting if we just make sure that the start of this string does not match the start of the sorted string, and the end of the string does not match the end of the sorted string. And as long as that's the case, then we're good. We're only counting this one unique possibility because basically this is the only way, this is kind of the most compressed, the smallest substring that can match this string. So that's what we do here. Basically for every string in the group, first of all, I sort the group so that I can binary search it. Now for every string in the group, we're going to iterate over every substring. The substring has to have a length of at least 2. If it's just 1, then sorting it doesn't change it. And now we're just going to sort in between I and j, and then we're just going to check string I not equal to other I, string j minus 1 not equal to other j minus 1, and other is in the group list. So this is funny because this is actually like length cubed log length because of all the loops we do. But it turns out this is okay because I already set up this for all but the biggest n. And so by the time we get to this case, length is actually quite small. Yeah, I haven't actually analyzed what the runtime is here, but it's probably some funny exponent. Actually, we can try to go for it. So basically what we know is that n times L is at most 285. We're gonna call, what do we want to call this? I don't know, T, the total length, 285. So n times L is at most T. And then we have 2 algorithms. Basically what we're doing is we're taking the minimum of 2 algorithms. One algorithm is n squared times L. And then the other algorithm is n times L cubed times log L. So we can pull out the NL here. And this is going to pull out into these. So this is T. So T times the min of these two. And this is the runtime of our algorithm. So essentially we want to minimize this by setting them to the same. And if that's the case, then L cubed log L equals T because, and what does that mean here? I guess it means L equals like T divided by log T to the, is that right? No, wait, maybe that's not right. Sorry. T to the 1/3 divided by log T. No, I was right earlier. Yeah, so L is that. Then L cubed is T over log T, and then log T and log L are basically the same within a constant. Yeah, so that is L. And then N is going to be, oh, that's super funny. To the 2/3 times log L, which is basically log T. So N is going to be equal to T to the 2/3 times log T to the 1/3. So this algorithm is actually T to the 5/3. It's just T times N because N equals L squared log L, which is going to be T to the 5/3 times log T to the 1/3. Okay, that is the runtime of this algorithm. So there we go. Yeah, and that's pretty cool. I don't think I've ever done this complexity before, but anyway, there you have it. Yeah, it turns out that the constant factor is really, really good because everything we're doing here, it's just some really basic string operations. So even though this number is probably kind of big, well, whatever. You know, yeah, something, you know, E9. Even though this is kind of big, the constant factor is really good. There's a lot of, you know, divided by 2s, maybe even divided by 3s going on here. So the constant factor is really, really good, and it's actually quite fast. My solution ran in something like 300 milliseconds. Yeah, and then there are things we can do, like we can improve this with like smart hashing algorithms and so on, but that makes the constant factor much worse, and I honestly think it's not worth it here in practice, because basically in the case where we're not doing this, I think that the length is actually really small. It's like less than Less than what? Less than like 30 even? Because yeah, if 25 divided by 200, yeah, it's about 30 at most. So cubic on 30 is fine. It's maybe even better than doing too many hash map things and hashing and so on. Anyway, yeah, I guess the contest just ended, so good timing there. And that's it for this one. Hope you found the problems, educational. I think that's what they're going for here. But anyway, yeah, if you like this, feel free to give me a like and subscribe, and I'll see you in the next video.